Every terrestrial simulation of Mars operates under a quiet, foundational compromise. The Earth is always waiting beneath the floorboards. In the sealed habitats of Hawaii's lava fields or the desert chambers of Texas, an emergency stop button remains within human reach. Real-time voice signals link directly to family members, and normal terrestrial gravity continues to anchor every physiological system. But when the first crew touches down on Utopia Planitia, that foundational compromise disintegrates. They will enter an environment defined not by temporary isolation, but by an irreversible physical shift. The human body, evolved over hundreds of millions of years under a dense atmosphere, a protective planetary magnetic umbrella, and a constant one-gravity load, must suddenly adjust to a world of thin carbon dioxide, toxic abrasive dust, and relentless subatomic radiation. Beyond the mechanical hazards lies a subtle, cumulative biological and psychological friction that no chamber on Earth can replicate. Colonizing Mars is not an engineering trial, it is an unbuffered biological transformation. If you value calm, evidence-based explorations of planetary science and human survival beyond Earth, consider subscribing. Staying connected ensures you won't miss upcoming deep dives into the physical realities of deep space. When an ocean voyager leaves port, the shore recedes, but the fluid mechanics of sea travel maintain a constant, reversible path. Turn the helm 180 degrees, and momentum carries the vessel back towards safety. Interplanetary trajectory physics operates under a far more unforgiving law. When a spacecraft executes its Trans-Mars injection burn, ignited at precisely the correct orbital juncture to escape Earth's gravitational sphere of influence, it commits to a hyperbolic escape trajectory governed entirely by celestial mechanics. The engines fire for a matter of minutes, consuming thousands of kilograms of propellant to impart a delta V of roughly 6 kilometers per second beyond low Earth orbit escape velocity. Once that burn concludes and the engines fall silent, the illusion of free maneuvering dissolves. There is no brake pedal in deep space, and there is no capability to turn the vessel around. To reverse direction would require an equivalent delta V burn that the spacecraft simply does not carry fuel to perform. The crew is not driving down a highway where they can choose an off-ramp. They are locked into an elliptical heliocentric transfer orbit, a Hohmann transfer path that dictates their physical movement across millions of kilometers of vacuum. Every meter of forward progress is dictated by Kepler's laws of planetary motion. This creates an immediate, profound psychological shift. On Earth, human exploration has always operated under the implicit assumption of physical agency, the belief that if conditions become unbearable, one can turn back. In interplanetary transit, celestial momentum acts as a massive physical trap. The spacecraft becomes a bullet fired from a planetary gun. Once it leaves the barrel, its path to the target is fixed by the curvature of gravity itself. As the days accumulate following Trans-Mars injection, the crew experiences a visual shift that no human eyes have ever witnessed across historical generations. During Apollo missions to the Moon, astronauts could block the Earth with a thumb raised to the window, but the planet remained a distinct, bright blue marble, a tangible sphere displaying familiar continents, swirling cloud decks, and glowing ocean basins. Across the 3-day transit to the Moon, Earth remained an omnipresent visual anchor, occupying a significant angular diameter in the sky. During a transit to Mars, however, the planet of human origin steadily shrinks over weeks into an insignificant point of light. Psychologists and aerospace medicine specialists define this transition as the Earth out of view phenomenon. As Earth contracts from a resolved disk into a dim blue star indistinguishable from the background stellar field, the subconscious human neural architecture undergoes severe strain. For millions of years, the visual persistence of Earth, its broad horizon, its changing daylight, its blue atmosphere served as an unshakable foundation for human psychological grounding. When that visual anchor vanishes into the cosmic void, the the brain loses its primary spatial reference frame. Astronauts in low Earth orbit aboard the International Space Station can look down every 90 minutes to see the familiar contours of home. Even lunar explorers could watch the Earth rise over the cratered horizon. But deep space transit strips away this visual umbilical cord. The psychological detachment is absolute. Looking out the quartz glass viewport reveals only an unchanging pitch-black abyss punctuated by unblinking stars, with home reduced to a pale blue speck indistinguishable from a distant sun. This visual vanishing forces a quiet, terrifying cognitive realization. Earth is no longer a world underfoot, but a memory lost in the expanse of space. To prepare crew members for this psychological reality, space agencies have conducted extensive isolation studies inside closed terrestrial habitats, such as the HIC's facility on the slopes of Mauna Loa or NASA's Chappell Chamber at the Johnson Space Center. Astronaut candidates spend months or even years living inside simulated Martian bases, breathing recycled air, wearing mock pressure suits during surface EVAs, and adhering to simulated communication delays. Yet every terrestrial simulation suffers from a fundamental, unbridgeable flaw: the omnipresence of a real-time safety net. No matter how strictly a Chappell crew adheres to simulation protocols, their subconscious minds remain aware that a thick atmosphere lies just outside the habitat walls, that medical technicians stand by a few hundred meters away, and that an emergency valve turn or hatch opening will instantly flood their lungs with ocean-fresh terrestrial oxygen. If a participant suffers a severe psychological crisis or a medical catastrophe, the simulation can be halted with a single phone call. True planetary isolation destroys this psychological safety net entirely. When a crew is 3 months into an interplanetary transit, floating midway between Earth and Mars, no emergency button exists. A catastrophic failure of the environmental control system or a severe neuropsychiatric breakdown cannot be resolved by aborting the mission. The physical reality of deep space enforces absolute self-reliance. The crew knows that no rescue vessel can be launched from Earth to intercept them. As orbital mechanics prevents fast-track rendezvous trajectories, terrestrial simulators can test operational discipline and interpersonal friction, but they can never simulate the existential terror of knowing that the physical environment outside the hull is absolute death, and that help does not exist anywhere within 50 million kilometers. This realization fundamentally alters the internal social dynamics of the crew. When returning home is physically impossible for a minimum of 2 to 3 years due to the alignment of planetary orbits, the small group of astronauts inside the spacecraft becomes an isolated biological island. In traditional terrestrial expeditions, interpersonal conflicts or personality clashes could be managed with the knowledge that the expedition had a finite end date, or that individuals could separate upon returning to base camp. On a Mars mission, the crew is locked together inside a pressurized cylinder no larger than a small townhouse, surrounded by lethal vacuum, with no possibility of escape or external intervention. Under these conditions, minor behavioral quirks or subtle communication breakdowns undergo massive psychological magnification. Social neuroscientists studying long-duration isolation note that prolonged confinement in hazardous environments triggers emotional withdrawal, heightened paranoia, and displacement of frustration onto ground controllers. But on a Martian voyage, the relationship with ground control itself fractures under light-speed transmission delays, as ground controllers become distant voices delayed by minutes. The crew's reliance on Earth authority breaks down. They are forced to form a self-contained social structure that must absorb extreme stress without structural failure. The psychological trap of the point of no return is not merely a mathematical reality of orbital mechanics. It is a continuous cognitive pressure that reshapes human consciousness. Long before the spacecraft reaches the atmosphere of Mars, the crew has ceased to function like earthbound professionals. They have stepped into a state of profound existential detachment, where survival depends entirely on maintaining emotional stability inside a metal shell hurtling through an indifferent void. This mental recalibration marks the end of transit mechanics and sets the stage for the physical, neurological toll of deep space. This psychological trap is rooted in the uncompromising laws of orbital mechanics. Once the spacecraft executes its Transmars injection burn, burning thousands of kilograms of propellant to break free from Earth's gravity well, the trajectory becomes mathematically locked. Unlike naval ships or aircraft that can turn back when weather turns foul or mechanical doubts arise, an interplanetary vehicle operates inside a high-energy Hohmann transfer ellipse. Reversing direction would require an equivalent rocket burn that the vessel simply does not have the fuel mass to execute. The hypergolic engines cut off, leaving the ship coasting along a ballistic arc governed entirely by solar gravity. Every passing minute carries the crew deeper into the void at over 11 kilometers per second relative to Earth. The physical impossibility of return transforms the spacecraft's internal environment from a temporary mission module into a permanent existential container. This acute orbital isolation fundamentally alters the psychological relationship between crew members and ground control. On Earth, high-stress environments like submarines or polar research stations maintain an implicit psychological bridge to home base. Operators know that emergency evacuations can be mounted if catastrophic structural failures occur. On an interplanetary trajectory, ground control is reduced to an advisory observer. When an onboard anomaly arises, whether a thermal loop leak, electrical short, or volatile gas spike, the crew must resolve the crisis immediately using only local tools and crew expertise. The awareness that no external rescue ship can be launched to intercept them creates a shift in crew governance. Decisions that were once deferred to mission controllers in Houston or Star City are made locally inside the flight deck, fostering an intense, insular group autonomy that forever separates the crew's operational culture from Earth control. Inside the pressurized hull of an interplanetary transit vessel, deep space is not silent. It is dominated by a continuous, low-frequency acoustic environment generated by life support machinery, the steady hum of air circulation fans, the rhythmic clack of carbon dioxide scrubbers, the whine of coolant pumps, and the vibration of attitude control gyroscopes. This permanent 60-decibel background drone becomes an inescapable sensory background. There are no natural soundscapes, no wind, no rain, no variations in atmospheric pressure to signal changing seasons. Combined with this acoustic monotony is a profound lack of spatial variation. The crew spends 7 months navigating a static volume of metallic corridors and padded quarters where every wall, hatch, and lighting array remains identical day after day. Beyond visual and acoustic monotony, microgravity immediately destabilizes human physiology by removing the downward gravitational vector. On Earth, gravity constantly pulls body fluids toward the lower extremities. In microgravity, blood and interstitial fluids shift upward toward the chest and head, displacing roughly 2 liters of fluid cephalad. Astronauts experience immediate facial puffiness, nasal congestion, and a sensation of head fullness as jugular veins distend and venous pressure inside the skull rises. This cephalad fluid shift is not a temporary inconvenience. It is the opening phase of a chronic biological reorganization. The human vascular system, evolved to push blood upward against Earth's gravity, finds itself overpressurizing the upper torso and brain. As hydrostatic pressure gradients disappear, the central nervous system must adapt to an environment where the internal pressure dynamics of the body are in constant, unbuffered tension with the artificial interior of the craft. As the months in deep space accumulate, this sustained upward fluid pressure begins to physically reshape the human brain and visual apparatus, a clinical condition known as spaceflight-associated neuroocular syndrome, or SANS. Without gravity to draw fluid downward, intracranial pressure remains chronically elevated, exerting continuous mechanical force against the back of the eyes and the brain's ventricles. The sheath surrounding the optic nerve swells with excess cerebrospinal fluid, compressing the nerve fibers that transmit visual data from the retina to the visual cortex. Over time, this mechanical compression causes optic disc edema, flattening the posterior globe of the eyeball and inducing hyperopic shifts that degrade visual acuity. Astronauts who departed Earth with 20/20 vision find their eyesight progressively blurring, unable to focus on close-up instrument displays without corrective lenses. Simultaneously, magnetic resonance imaging of astronauts following long-duration spaceflight reveals that the brain physically shifts upward within the skull cavity. The CSF-filled space at the vertex of the brain contracts, while the cerebral ventricles expand by up to 20% to accommodate the altered fluid distribution. The internal venous structures of the neck and head remain engorged, impairing normal cerebral venous drainage. This structural crowding inside the rigid bony vault of the cranium is not merely an anatomical curiosity, it directly threatens neurological performance. The continuous pressure on delicate neural pathways and optic structures means that as crew members travel further into the interplanetary void, their physical capacity to visually inspect navigation panels and process complex spatial information is steadily compromised by the very fluids that keep them alive. The neurological impact of deep space transit extends far beyond fluid dynamics into the domain of brain structural plasticity and sensory integration. On Earth, the human brain continuously processes a rich stream of sensory inputs changing thermal gradients, complex ambient sense, gravitational tilt detected by the inner ear's otolith organs, and varying visual depths. In microgravity confinement, this sensory stream is severely impoverished. The otoliths, calibrated to detect the down vector of gravity, become functionally silent or produce conflicting signals when the head moves, causing sensory conflict between visual inputs and vestibular feedback. To cope with this ambiguity, the brain undergoes neuroplastic reorganization, down-regulating vestibular signaling and relying almost exclusively on visual cues to establish an arbitrary sense of up and down. Functional MRI studies show altered connectivity within the motor cortex, vestibular processing centers, and the default mode network. This neural rewiring occurs in an environment characterized by sensory deprivation syndrome. Without the rich environmental complexity of Earth, the neural circuits responsible for stress regulation, spatial memory, and cognitive flexibility begin to degrade. Dendritic spine density in hippocampus regions, vital for memory formation and spatial navigation, can contract under chronic stress and lack of novel environmental stimulation. The brain becomes functionally specialized for an artificial low-stimulus environment, optimizing itself for microgravity survival at the expense of terrestrial adaptability. Before the spacecraft even approaches its destination, the crew's central nervous system has undergone profound structural modification, leaving them neurologically altered long before their boots touch alien soil. After 7 months of microgravity transit, fluid congestion, optic nerve swelling, and vestibular rewiring, the crew faces one of the most dangerous phases of the mission, transitioning from zero gravity to an alien gravity well. The human body, having spent over 200 days shedding bone mineral density, losing muscular strength, and recalibrating its cardiovascular reflexes to microgravity, is suddenly subjected to the violent deceleration forces of Martian atmospheric entry. During entry, descent, and landing, entry vehicle deceleration generates G-forces that push blood away from the head, back down toward the lower body. For a crew suffering from cardiovascular deconditioning and reduced blood plasma volume, this sudden shift triggers severe orthostatic intolerance. Upon touchdown, as the spacecraft comes to rest on the surface of Mars, the crew must immediately adapt to 0.38 Earth gravity. The inner ear otoliths, suppressed for months, are suddenly flooded with gravitational signals, triggering acute spatial disorientation, nausea, and motion sickness. Muscles that have atrophied and bones that have lost up to 10% of their density must suddenly support body mass again. A crew that has been neurologically and physically weakened by long-duration deep space transit must now step out into an unforgiving environment where physical stamina and sharp motor control are mandatory for survival. The deep space silence of transit concludes not with gentle rest, but with a violent biomechanical shock as debilitated humans land on an alien world, only to face an immediate surface hazard waiting outside the airlock. Inside the central nervous system, this prolonged zero-gravity state triggers profound anatomical restructuring. Without gravitational pull-drawing fluid toward the lower limbs, roughly 2 liters of venous blood and interstitial fluid shift upward into the chest and head. This cephalad fluid redistribution elevates central venous pressure and increases intracranial pressure, pushing fluid against the back of the eyes. Over months of deep space transit, optic nerve sheaths expand, optic discs swell, and the posterior globe of the eye flattens a condition known as spaceflight-associated neuroocular syndrome. Astronauts experience progressive hyperopic shifts, visual field distortions, and chorioretinal folds. Simultaneously, the vascular endothelium inside cerebral veins adapts to constant hypertension, altering local blood-brain barrier permeability. Without the natural circadian mechanical cues of Earth's gravity and natural sunlight, cerebral venous drainage slows down, altering fluid dynamics within the brain's ventricles. The brain physically shifts upward inside the skull, compressing cortical tissue against the inner cranial vault. The silent transit through deep space is not a passive waiting period. It is an ongoing neurological remodeling that alters how human eyes see and how human brains process spatial reality. Beyond fluid redistribution and SANS, long-duration microgravity induces neuroplastic rewiring within the brain's sensory motor cortices and vestibular pathways. Without a constant downward gravitational vector to anchor spatial orientation, the brain downregulates otolith signals from the inner ear and relies almost exclusively on visual and tactile cues to construct its internal model of up and down. Neuroimaging studies of long-duration spaceflight show structural changes in white matter tracts connecting the cerebellum, parietal cortex, and motor cortex. The brain physically remaps its locomotor and postural control algorithms. When crew members close their eyes in microgravity, they frequently experience illusionary sensations of spinning or falling through infinite space, as the unanchored vestibular system generates phantom motion signals. This neurological adaptation, while essential for functioning in zero-G, leaves the crew's motor control system severely compromised when they finally re-enter a planetary gravity environment. The descent to the Martian surface, often called the 7 Minutes of Terror, is a brutal kinetic deceleration sequence that compresses months of physical stability into a violent encounter with gravity. Entering the Martian atmosphere at speeds exceeding 20,000 kilometers per hour, the lander relies on aerodynamic drag against a thin carbon dioxide atmosphere to shed 99% of its kinetic energy. Superheated plasma envelopes the heat shield, subjecting the vessel and its occupants to deceleration forces reaching 5 to 8 G-loads. For a crew whose blood vessel walls have relaxed, and whose cardiovascular reflexes have grown dormant during 7 months of microgravity, this sudden acceleration vector acts as a physical sledgehammer. Blood is forcibly driven away from the brain into the lower limbs, causing immediate tunnel vision, grey-outs, and potential loss of consciousness. As the heat shield separates and supersonic retropropulsion thrusters ignite blasting supersonic jets of cold gas and fiery exhaust toward the approaching reddish terrain, the deceleration vector shifts abruptly. The sudden, violent transition from freefall weightlessness to intense, multidirectional G-forces forces fluid to rapidly redistribute back across the vascular tree. Blood pressure spikes erratically, heart rates surge to near maximum capacity, and the vestibular apparatus experiences violent mechanical shearing forces. the vehicle slams through the lower atmosphere, maneuvering through low-density dust layers until the sky crane or landing legs make contact with the soil. The roaring thrusters cut out, leaving a sudden, absolute stillness. But as the mechanical vibration subsides, the occupants inside the pressurized cabin are not greeted by relief. They're instantly exposed to a permanent physical force they have not felt in nearly 3/4 of a year, the relentless downward pull of planetary gravity. Stepping out of the landing module seats onto the floor deck marks the onset of acute orthostatic intolerance and severe vestibular disruption. Although Mars possesses only 38% of Earth's gravitational pull, meaning a 70-kilogram astronaut weighs just 26 kilograms on a Martian spring scale. This partial gravity does not feel like lightness or effortless mobility. To a body acclimatized to microgravity, 0.38 g feels like an oppressive, disorienting drag. When an astronaut attempts to unbuckle their harness and stand upright, the baroreceptor reflexes responsible for maintaining blood pressure fail to adjust rapidly. Blood instantly pools in the splanchnic circulation and lower extremities, causing a sudden drop in cerebral perfusion pressure that triggers acute dizziness, nausea, and presyncope simultaneously, the otolith organs inside the inner ear having recalibrated to zero-gravity sensory cues send chaotic, contradictory signals to the brain upon detecting the downward gravitational vector. Every micro-movement of the head creates a false sensation of pitching forward or tumbling sideways, a condition known as space motion sickness operating in reverse. Muscle groups that have undergone atrophy, particularly the anti-gravity postural muscles of the calves, quadriceps, and lower back, are suddenly called upon to stabilize the body against structural collapse. Joints and spinal discs, which expanded in microgravity as intervertebral cartilages absorbed fluid, are compressed back together under the new weight load. Stepping onto the Martian soil in a heavy pressure suit demands immense physical effort. Every stride requires deliberate cognitive control as the brain struggles to coordinate weakened muscles with a disoriented balance system. Terrestrial popular science often portrays 38% Earth gravity as a benign compromise, a comfortable environment where humans can leap higher, carry heavier equipment, and move with agile grace. This assumption represents a fundamental biomechanical misconception. In reality, 0.38 g is a disorienting physical middle ground that the human body was never evolutionarily programmed to inhabit. Earthborn human physiology is strictly binary. It evolved to function either under a full one-gravity load or, in modern spaceflight, to temporarily survive in zero gravity. It possesses no innate metabolic sensor or regulatory feedback loop calibrated specifically for 38% gravity. Biomechanical gait analysis reveals that walking on Mars alters natural human movement kinematics. The normal human pendulum gait, where potential and kinetic energy are smoothly exchanged with each step, breaks down under low gravity. Foot-ground contact times increase. Stride frequencies drop, and the center of mass moves unnaturally, placing strange torsional stresses on hip and knee joints. Furthermore, neurovestibular readaptation to partial gravity proceeds at an agonizingly slow pace. On Earth, the brain relies on a clear 1G baseline to resolve balance ambiguities. On Mars, the weak gravitational signal is constantly drowned out by the noise of voluntary body movement, prolonging spatial disorientation for weeks. Cardiovascular recalibration is equally problematic. 38% gravity is insufficient to fully prevent ongoing bone mineral loss or cardiovascular deconditioning, yet strong enough to cause continuous fluid pooling in the lower body. Rather than offering a welcoming habitat, Martian gravity establishes a permanent biomechanical mismatch, a gravity well strong enough to strain a weakened body, but too weak to keep human bones and hearts intact over time. As the crew slowly adjusts to standing, moving, and operating inside their pressurized habitat decks under Martian gravity, their immediate survival shifts from internal physiology to external environmental defense. The moment the lander touched down, its high-velocity engine exhaust kicked up thousands of cubic meters of fine, orange-red Martian dust, blanketing the landing pad and coating the exterior hatches of the spacecraft. As crew members prepare for their initial surface extravehicular activities, they look out the habitat viewports to see a dry, desolate plain swept by faint atmospheric winds under a butterscotch sky. The surface appears placid, but the soil beneath their landing legs harbours a quiet, destructive chemical threat. The ultrafine dust particles settling over the airlock seals and solar collectors are not merely fine sand, they are chemically reactive, electrically charged, and mechanically abrasive particulates waiting to adhere to every fabric seam and mechanical joint. The violent transition to 0.38 G delivered the first physical shock to human biology. Now, the landing has placed the crew inside an environment where the very soil beneath their boots is actively hostile to mechanical hardware and human tissue alike. The physical strain of entry and landing concludes, yielding immediately to the relentless microscopic siege of Martian dust chemistry. This biomechanical disorientation is further intensified by aerodynamic and sensor and motor disruption during entry, descent, and landing. As the lander slams into the thin Martian atmosphere at hypersonic speeds, atmospheric friction generates intense shock waves and severe deceleration loads. Supersonic retro-propulsion engines ignite, blasting high-velocity exhaust plumes into incoming airstreams to stabilize the descent. Inside the cockpit, crew members experience sudden G-load spikes that drive blood away from their brain, threatening transient loss of consciousness just as precision piloting is required. When the vehicle finally touches down and G-forces drop from entry peaks to 0.38 Earth gravity, the vestibular system suffers immediate sensory mismatch. The otolith organs in the inner ear, calibrated for Earth gravity and then suppressed by months of microgravity, send chaotic signals to the brainstem. Simple head movements trigger illusions of tumbling or tilting, while skeletal muscle stretch receptors fail to register expected postural resistance. Walking across the habitat floor requires conscious biomechanical concentration, as the foot strike force and joint stabilization kinetics under 38% gravity differ fundamentally from both zero-G weightlessness and terrestrial locomotion. The physiological strain of touchdown is further compounded by extreme cardiovascular reflex suppression and orthostatic hypertension. During 7 months in microgravity, blood vessels lose their vascular tone, and the autonomic nervous system downregulates baroreceptor sensitivity because it no longer needs to pump blood against gravity. Upon standing in 38% gravity, venous blood pools rapidly in the lower abdomen and legs. Cerebral perfusion pressure drops precipitously, causing severe presyncope, tunnel vision, and cognitive impairment just as the crew must execute critical post-landing procedures. Astronauts cannot simply unbuckle their harness, step out of the lander and begin surface activities. They must spend hours lying supine in pressurized flight seats, consuming rehydration fluids and wearing lower body compression garments to force blood back into cerebral circulation, while their autonomic nervous system gradually relearns how to regulate arterial pressure against gravity. On Earth, dust is largely anodyne, composed of rounded grains of weathered quartz, organic fibers, and soil detritus softened by liquid water and atmospheric erosion. On Mars, where liquid water has been absent for billions of years and physical weathering is driven by atmospheric winds and micrometeoroid impacts, dust is a completely different physical species. Martian regolith dust consists of extremely fine, unweathered mineral fragments with average particulate diameters smaller than 5 microns, fine enough to remain suspended in the thin carbon dioxide atmosphere for months. Under microscopic examination, these tiny grains display sharp, jagged edges, razor-like crystalline structures, and high surface area ratios. They act not like soft terrestrial soil, but like pulverized glass. But the physical morphology of Martian dust is only its most benign characteristic. Its chemical composition presents an aggressive toxic hazard. The surface regolith is heavily impregnated with chlorine salts in the form of calcium, magnesium, and sodium perchlorates, present in concentrations ranging from 0.5 to over 1% by weight. On Earth, perchlorates are synthetic industrial oxidizers used in solid rocket propellants and munitions. On Mars, they are naturally synthesized by ultraviolet radiation interacting with atmospheric chlorine compounds. When human explorers step out onto the reddish surface, they are not walking on benign sand, but on a vast planet-wide bed of chemically reactive, highly abrasive industrial oxidizers. This microscopic dust settles into every microscopic surface crevice, coats the exterior fabrics of extravehicular pressure suits, and clings stubbornly to metal airlock hatches, ready to break through habitat defenses. The true biological threat of Martian dust materializes the moment an astronaut returns from a surface extravehicular activity and steps into the habitat airlock. As the airlock pressurizes and suit outer garments brushed clean by mechanical brushes, off-gas, dust particles inevitably escape mechanical containment, entering the living quarters atmosphere. Inhaled into the human respiratory tract, particles smaller than 2.5 microns bypass the upper airway's mucosal filters and penetrate deep into the pulmonary alveoli. The sharp, glass-like morphology of the crystalline silicate particles causes mechanical microabrasions in delicate lung tissue, triggering chronic inflammatory responses, alveolar macrophage destruction, and progressive pulmonary fibrosis, a condition functionally identical to terrestrial silicosis or coal workers' pneumoconiosis. Simultaneously, the chemical toxicity of inhaled perchlorates begins to systematically disrupt human endocrine function. Once absorbed across the alveolar membrane into the bloodstream, perchlorate ions competitively inhibit the sodium iodide symporter protein in the thyroid gland. This blocks the thyroid's ability to absorb essential iodine, halting the synthesis of thyroid hormones triiodothyronine and thyroxine. The resulting systemic hyperthyroid state leads to chronic fatigue, metabolic slowing, thermal dysregulation, severe cognitive blunting, and long-term metabolic disruption, even with advanced HEPA filtration, multi-stage airlock washdowns, and suit port entrance systems where pressure suits remain outside the habitat. Fine Martian dust continuously finds pathways inside. It becomes a permanent, invisible chemical contaminant circulating through the closed environmental life support system, quietly poisoning crew members with every breath. Beyond its biological toxicity, Martian dust poses an inescapable mechanical threat driven by atmospheric physics and electrostatic forces. Because the Martian atmosphere is extremely dry and low density, hovering around 6 millibars wind-blown dust particles experience intense triboelectric charging as they collide with one another and scrape across the planet's desiccated surface. Each grain carries a strong electrostatic charge. When an astronaut walks across the terrain or a mechanical rover drives over regolith, the friction generates powerful local electrostatic fields. This electrostatic cling causes dust particles to bond tenaciously to synthetic spacesuit fabrics, optical viewports, rubber suit seals, and metallic surfaces. Traditional cleaning methods like air jets or mechanical brushes fail to dislodge electrostatically bonded dust. Brushing often increases triboelectric charge, causing particles to snap back onto the surface with greater force. Once attached to suit joints and airlock seals, the abrasive grains act as an aggressive grinding compound. Every time an astronaut flexes a suit elbow or rotates an airlock latch, the sharp mineral particles score precision metal surfaces, wear down elastomer seals, and degrade pressure integrity. On solar collectors, electrostatically attached dust forms an opaque film that degrades power output, by up to 1% per day during regional dust events, steadily starving the habitat of energy. Martian dust is not an environmental background detail. It is an active mechanical abrasive that relentlessly erodes the seals, bearings, and optical sensors keeping the habitat alive. This constant fight against dust contamination reshapes crew daily routines and imposes a heavy psychological toll on surface operations. What was envisioned as an exciting era of surface exploration quickly degenerates into an endless series of tedious maintenance rituals. Astronauts must spend hours after every EVA performing meticulous airlock decontamination, inspecting pressure seals with microscopic cameras, scrubbing suit port interfaces, and replacing worn mechanical seals. Every piece of equipment brought inside must be chemical washed, and every air filter must be continuously monitored for perchlorate saturation. The psychological impact of living in an environment where every surface outside is coated in invisible chemical poison creates pervasive anxiety. Crew members become hypervigilant, obsessed with minor dust traces inside their living quarters, knowing that a single breached seal or failing air filter could lead to chronic lung disease or habitat depressurization. The initial excitement of standing on an alien world dissolves into the reality of living inside an industrial cleaning operation. The planet outside is not a realm of boundless discovery, but a dusty biohazard zone that must be constantly repelled. As astronauts spend their days scrubbing airlock thresholds and monitoring suit seals, they look out the habitat viewports at the reddish horizon, only to realize that the optical environment itself is beginning to alter their perception of space and time. The physical siege of toxic dust transitions into the psychological alienation of the Martian horizon. The chemical aggression of Martian regolith extends deep into human cell biology and material science. The fine, airborne dust covering the plains contains high concentrations of calcium and magnesium, perchlorate's highly reactive chlorine-oxygen compounds that act as powerful endocrine disruptors. When trace dust particles bypass airlock filtration and enter habitat air, perchlorate ions dissolve in mucosal fluids and bind to sodium iodide symporter proteins in human thyroid glands. This competitive inhibition blocks iodine uptake, disrupting thyroid hormone synthesis and triggering metabolic suppression, metabolic fatigue, and systemic temperature dysregulation. At the mechanical level, sub-micron regolith particles possess razor-sharp, unweathered basaltic glass geometries due to the absence of liquid water erosion on Mars. These microscopic shards act as aggressive abrasives, subjected to dry atmospheric conditions. The dust accumulates strong electrostatic charges through triboelectric friction, causing it to cling tenaciously to spacesuit fabrics, solar panel glass, and synthetic airlock seals. As airlock hatches cycle open and closed, electrostatic dust particles grind into Viton pressure seals and rotary joint bearings, cutting microgrooves that cause slow atmosphere leaks and accelerating mechanical degradation of suit joints. The physical challenge of dust mitigation is further escalated by atmospheric triboelectric dynamics and mechanical seal erosion. During Martian dust storms, winds exceeding 100 km per hour sweep dust particles across the dry, ungrounded planetary surface. Frictional contact between airborne particulates generates high electrostatic charges, turning dust clouds into electrically charged plasma-like plumes. When crew members perform extravehicular activities, their suit fabrics accumulate thousands of volts of static charge relative to the habitat environment. Upon re-entering the airlock, electrostatic forces attract fine dust deep into woven suit fibers, zipper tracks, and airlock pressure seals. As suit joints flex under pressure, abrasive basaltic shards cut through polymer coatings, degrading gas-tight integrity. Habitat maintenance protocols require continuous ultrasonic cleaning of suit interfaces and chemical wiping of pressure bulkheads, turning daily life into an unyielding battle against microscopic mechanical erosion. When humans look out across a landscape on Earth, the visual environment is saturated with familiar optical cues calibrated by terrestrial atmospheric optics and geometry. On Mars, the visual landscape undergoes a surreal distortion. Because Mars orbits the Sun at an average distance of 228 million kilometers, roughly 1.52 astronomical units from the Sun's solar irradiance on the surface, drops to just 44% of terrestrial levels. The Sun appears not as a warm, expansive gold disk in the sky, but as a small, intense, distant point of light that provides no felt radiant warmth. Atmospheric lighting is permanently subdued, casting an eerie, twilight-like illumination even at local solar noon. Furthermore, the daytime sky does not display the familiar Rayleigh scattered azure blue of Earth. Instead, fine iron oxide dust suspended in the thin carbon dioxide atmosphere selectively absorbs blue light and scatters red wavelengths, painting the daytime sky in an oppressive monochrome butterscotch or yellowish-brown hue. At dusk, this optical situation undergoes an inverted transformation. As the small sun sinks toward the horizon, its light passes through a longer path length of dust-laden atmosphere. The fine dust particles, roughly matching the wavelength of visible light, execute forward Mie scattering, allowing blue light to pass through while scattering red light away from the line of sight. The result is a cold, eerie blue glow surrounding the setting sun against a dark brown sky. For human explorers accustomed to warm orange sunsets under a blue sky, standing under a butterscotch sky with a cold blue sunset produces a profound visual and perceptual disconnect, signaling continuously to the subconscious mind that this world is fundamentally alien. This optical dissonance triggers a deep psychological state known as solastalgia, an acute form of distress caused by environmental transformation and the complete absence of familiar natural biological cues. On Earth, human mental health is subtly sustained by constant visual and auditory inputs, the green hues of chlorophyll-rich foliage, the changing reflection of liquid water bodies, the movement of clouds carrying moisture, and the complex scent profiles of soil and vegetation. On Mars, every natural biological cue is zero. The terrain outside the habitat viewport is a static, sterile expanse of dark basalt rocks, rust-coloured regolith dunes, and sharp volcanic rills under a dim, dust-choked sky. There are no trees, no streams, no birds, and no seasonal shifts beyond long, frigid dust storms that blot out the distant sun for months at a time. Psychological evaluations of polar researchers living in Antarctica during the polar night reveal that visual monotony and the absence of natural greenery induce severe depression, emotional blunting, and an explosive rise in interpersonal friction. On Mars, this sensory deprivation is magnified by the knowledge that no green landscape exists anywhere on the entire planet. The human mind, co-evolved over evolutionary epochs alongside lush terrestrial ecosystems, experiences a continuous or quiet grief when confronted with a universe reduced to endless shades of red and brown. Living inside pressurized modules, astronauts look out at a world that feels not merely uninhabited, but profoundly hostile to the concept of life itself, stripping away the unconscious visual comfort that Earthborn humans rely on for emotional equilibrium. Beyond the colour spectrum of the sky and the sterility of the terrain, the physical geometry of the Martian horizon introduces a subtle, disorienting spatial illusion. Mars is a significantly smaller planetary body than Earth, possessing a mean volumetric radius of 3,389 kilometres, roughly 53% of Earth's 6,371 kilometre radius. Because the planet's surface curves far more sharply than Earth's, the visual horizon is physically much closer to an observer. For an astronaut standing on a flat Martian plain with an eye level of 1.8 metres, the visual horizon lies just 3.4 kilometres away, compared to 4.7 kilometres on Earth. On a vast, featureless volcanic plain like Olympus Mons or Chryse Planitia, this shortened visual radius creates a disorienting sensation that the ground is dropping away precipitously just beyond the near distance. The landscape appears squeezed, as though the observer is standing on a small spherical mound suspended in space rather than a broad, expansive world. When combined with the lack of atmospheric haze which on Earth provides depth perception by causing distant mountains to appear fainter, Martian landforms miles away appear deceptively sharp and close, while remaining geometrically unreachable within expected walking times. This breakdown of terrestrial spatial cues disrupts the brain's internal mapping systems, causing persistent spatial disorientation and a claustrophobic sense that the horizon is closing in around the observer, reinforcing the psychological realization that they are trapped on a tiny, alien sphere. This visual and spatial isolation inside pressurized habitats directly forces the crew to confront their absolute physical exposure to the space environment, because the atmosphere is far too thin to provide optical or thermal buffering. Crew members spend up to 95% of their surface mission confined inside buried habitat modules or shielded pressurized rovers, looking out at the miniature horizon through multi-layered quartz viewports. But as they remain tucked behind thick habitat walls to escape the psychological toll of the desolate exterior landscape, they must confront an invisible, far more dangerous physical reality that passes through metal and rock alike. The thin atmosphere that creates butterscotch skies and blue sunsets offers zero meaningful barrier against high-energy subatomic radiation streaming from the cosmos. The psychological alienation of the horizon is merely the visual shell of a world where subatomic particles continuously bombard the surface. As the crew retreats underground to protect their minds from the desolate visual void, they step directly into a fight against chronic nuclear degradation. The optical crisis of the Martian horizon yields inevitably to the subatomic ledger of surface radiation. This perceptual distortion is compounded by the altered atmospheric optics and compact visual geometry of the Martian environment. Because Mars orbits farther from the Sun, the surface receives only 44% of the solar energy that strikes Earth, creating a pale, perpetual twilight atmosphere. Airborne sub-micron iron oxide dust particles scatter sunlight through Mie scattering, absorbing blue wavelengths while forward scattering reddish-orange light during the day. This fills the sky with a dull butterscotch hue, but at sunset, the optical process reverses light passing through the long atmospheric path scatters red light away, leaving a pale, violet-blue halo glowing around the shrinking solar disk. Furthermore, because Mars has a radius nearly 50% smaller than Earth's, the planetary curvature drops away far more rapidly. On Earth, a standing observer sees a horizon nearly 5 kilometers distant. On Mars, the visual horizon contracts to just 3.4 kilometers. This closer, rapidly curving horizon creates a subtle optical claustrophobia, the sensation of standing atop a small, isolated dome surrounded by an empty sky. The visual environment offers no lush greens, no liquid reflections, and no vast terrestrial distances, trapping the human mind inside an alien visual sphere that continuously reinforces its absolute distance from Earth. The psychological impact of this visual alienation is intensified by circadian rhythm disruption and spectrum-deprived lighting. A Martian day, or sol, lasts 24 hours, 39 minutes, and 35 seconds. While a 39-minute daily shift seems minor, it continuously desynchronizes human circadian pacemaker neurons in the suprachiasmatic nucleus. Compounded by the dim, orange-shifted solar spectrum passing through heavy dust layers, the human body fails to receive the strong blue spectrum light cues required to suppress melatonin production during waking hours. Settlers experience chronic circadian phase delays, leading to sleep fragmentation, metabolic dysregulation, and persistent fatigue. Looking out through habitat viewports into a dim, butterscotch sky provides no natural psychological reset, forcing the crew to rely on artificial blue-spectrum light banks to maintain physiological alertness inside their subterranean living quarters. On Earth, human life is shielded from the lethal radiation environment of space by two massive planetary defense systems, a powerful intrinsic magnetosphere generated by the liquid iron outer core, and a dense atmosphere providing mass shielding equivalent to 10 meters of liquid water or a 1-bar pressure column. Mars possesses neither safeguard. The Martian intrinsic dynamo shut down roughly 4 billion years ago, leaving behind only weak, patchy, remnant crustal magnetic fields in the southern highlands. Furthermore, the Martian atmosphere is extremely thin, exerting a surface pressure of only 6 millibars, less than 1% of Earth's sea level pressure, which provides less than 20 grams per square centimetre of atmospheric column mass overhead. Consequently, the surface of Mars is flooded by two distinct, continuous sources of ionizing radiation, solar particle events composed of high-energy protons ejected during coronal mass ejections, and galactic cosmic rays originating from ancient supernova remnants outside the solar system. Galactic cosmic rays consist of relativistic atomic nuclei, ranging from single protons to heavy ions stripped of their electrons, known as HZE ions, travelling at near light speed. Dosimeter data from NASA's Curiosity rover RAD instrument confirms that an unshielded human on the Martian surface receives an average daily radiation dose of roughly 0.67 millisieverts per day. Across a typical 500-day surface stay, this equates to an accumulated dose exceeding 330 millisieverts, equivalent to receiving a full-body chest CT scan every 5 days for over a year and a half. When relativistic galactic cosmic rays collide with the thin Martian atmospheric column and strike the solid regolith surface, a secondary highly insidious radiation process occurs. High-energy HZE ions and protons do not simply pass through mineral matter. They collide directly with atomic nuclei in the basaltic rock and carbon dioxide gas, triggering nuclear spallation reactions. The primary cosmic particle shatters target atomic nuclei, releasing a shower of secondary subatomic debris, including energetic neutrons, secondary protons, gamma rays, and pi mesons. Secondary neutrons are particularly dangerous to human biological tissue. Uncharged subatomic particles. Neutrons do not interact with electron shells. Instead, they penetrate deep into matter until they collide head-on with light atomic nuclei, such as hydrogen atoms in human water molecules and cellular structures. This process, known as albedo neutron scattering, generates a dense secondary radiation field rising upward from the Martian soil itself. An astronaut walking on the surface is caught in a lethal subatomic sandwich hit from above by primary cosmic rays and hit from below by secondary neutron showers radiating from the ground. Inside human cells, these high-energy particles cause double-strand DNA breaks, complex cluster lesions that overwhelm cellular repair enzymes, and systemic oxidative stress. Over months of exposure, this chronic subatomic bombardment drives up lifetime cancer risks, damages central nervous system microvasculature, accelerates cognitive decline, and triggers premature cataracts and microvascular endothelial damage across every organ system. This unbuffered surface radiation environment completely upends traditional terrestrial architecture and exposes a profound engineering limitation. Lightweight inflatable habitats, glass viewports, and surface-mounted modules, staples of science fiction illustrations, are physically useless for long-term radiation protection. Passive shielding materials obey a mass law to absorb relativistic galactic cosmic rays and stop secondary neutron showers. Massive aerial density is required to reduce the annual surface radiation dose to acceptable career limits. Habitat roofs must be covered by a layer of compressed Martian regolith, at least 2 to 3 meters thick, or habitats must be constructed deep within natural subsurface structures like basaltic lava tubes. This necessity forces a fundamental cognitive shift in how planetary settlement is understood. Human explorers on Mars will not live in bright, sunlit surface domes looking out over sweeping red vistas. They will be forced to live underground, becoming subterranean cave dwellers inhabiting dark, buried vaults beneath meters of dense rock. Surface access will be strictly rationed based on personal radiation ledgers, where every minute spent outside the shielded habitat adds to an individual's accumulated sievert count. Living underground eliminates natural sunlight, severs the visual connection with the outside sky, and enforces a perpetual subterranean lifestyle that magnifies the psychological strain of isolation, turning the dream of walking on another world into a lifelong existence inside a buried concrete bunker. This demand for subsurface habitat burial creates complex engineering and biological feedback loops inside the closed ecology of the colony. To survive chronic radiation, humans must retreat behind thick regolith shields, but in doing so, they completely isolate their internal habitat environment from natural outdoor air exchange, thermal venting, and ambient light. The buried habitat becomes a tightly sealed, hyper-recycled biological pressure cooker. Air must be continuously scrubbed by mechanical devices, water must be purified through high-pressure membrane arrays, and food must be grown under artificial LED arrays using hydroline farming systems. Within this completely artificial underground biosphere, human biology is not only isolated from cosmic rays, but also severed from the vast, diverse microbial ecosystems of Earth. As crew members spend months inside buried modules breathing sterile, filtered air, their internal biological loops begin to interact with a microecosystem that is rapidly mutating under ambient habitat conditions. The fight against subatomic radiation forces humans into a sealed subsurface cage, setting the stage for a silent biological crisis taking place inside the human gut and habitat air ducts. The subatomic radiation ledger transitions directly into the biological paradox of the sealed biosphere. The subsurface radiation environment introduces complex nuclear physics constraints that dictate every aspect of habitat architecture. Because Mars lacks an intrinsic global magnetic field and possesses atmospheric surface pressure of only 6 millibars, high-energy galactic cosmic rays relativistic atomic nuclei, stripped of their electrons, pass through the atmosphere almost completely unattenuated. When these relativistic iron and carbon ions strike the upper layers of Martian regolith, they initiate nuclear spallation reactions. Relativistic ions smash directly into silicon iron and oxygen atomic nuclei in the surface soil, splitting them apart and creating dense showers of secondary neutrons, protons, and gamma-ray photons. This secondary neutron albedo bounces upward from the soil, creating a subsurface radiation field that can be even more biologically damaging than primary cosmic rays. Surfacing habitats with thin metal or polymer shields actually worsens radiation exposure, as incoming cosmic rays generate cascade showers of secondary radiation inside dense shield walls. To achieve effective shielding, habitat designs must utilize thick overburdens of hydrogenous materials and compacted regolith, at least 2 to 3 meters deep. Living on Mars requires descending beneath the soil, forcing settlers into an underground subterranean lifestyle, where natural sunlight is replaced by artificial LED cycles and external views are restricted to remote camera feeds. To protect against solar particle events and high-energy galactic cosmic rays, habitat engineering relies on multi-layered subsurface regolith shielding and hydro-rich materials. During intense solar particle events when coronal mass ejections hurl relativistic proton fluxes across interplanetary space, unshielded surface radiation doses can exceed several sieverts over a few hours, causing acute radiation sickness, tissue necrosis, and death. To mitigate this hazard, habitat structures are buried beneath 3 to 5 meters of compacted Martian regolith, often reinforced with water walls and polyethylene lining to absorb secondary neutrons. living beneath meters of soil shields human DNA from ionizing damage, but it transforms daily life into an entirely subterranean existence. Settlers spend their years inside windowless pressurized vaults, surrounded by concrete bulkheads and artificial lighting, completely severed from any direct visual contact with the sky above. Inside the buried habitat modules of a Martian settlement, human biology encounters an invisible ecological crisis. On Earth, human health is deeply integrated into a vast, open terrestrial microbiome. Every breath of outdoor air, every contact with natural soil, and every ingestion of fresh organic food exposes the human body to trillions of benign bacteria, fungi, and viruses that continuously train the immune system and maintain microbial diversity across the skin, respiratory tract, and gastrointestinal canal. On Mars, this environmental microbial reservoir is zero. The habitat interior is a hyper-sanitized, closed, artificial ecosystem where air is continuously passed through high-efficiency particulate filters. Water is repeatedly boiled and distilled through catalytic oxidizers, and surfaces are aggressively scrubbed with chemical disinfectants to prevent perchlorate accumulation and mold growth. As a result, the crew lives in an environment characterized by extreme microbial impoverishment. Without continuous exposure to diverse environmental microbes, the human gut microbiome undergoes progressive simplification over months of isolation. Beneficial commensal bacterial strains such as Faecalibacterium prausnitzii and Bifidobacterium species decline in abundance due to monotonous freeze-dried diets and sterile living conditions. This condition, known as gut dysbiosis, leads to systemic low-grade inflammation, impaired nutrient absorption, breakdown of the intestinal mucosal barrier, and severe immune system dysregulation. The crew is not merely living inside a sterile steel box. Their internal biological ecosystems are decaying from a lack of ecological contact with the natural world. While beneficial microbial diversity collapses inside the sterile habitat, opportunistic bacteria and fungi carried by the crew experience a dramatically altered evolutionary environment. Within the sealed environmental control loops, high humidity and hygiene compartments, warm temperatures, and elevated ambient radiation levels create an ideal breeding ground for fast-reproducing microbial strains. Microorganisms inside space habitats undergo accelerated mutation rates due to secondary neutron exposure and cosmic rays that penetrate partial shielding. Research conducted aboard the International Space Station demonstrates that opportunistic pathogens such as Staphylococcus aureus, Pseudomonas aeruginosa, and Aspergillus fumigatus exhibit heightened virulence, enhanced antibiotic resistance, and aggressive biofilm formation under long-duration spaceflight conditions. These mutating bacteria colonize the interior surfaces of water recycling lines, air ducts, and heat exchangers, forming dense, rubbery biofilms that resist chemical disinfection and physically clog precision fluid valves. Simultaneously, human immune defenses undergo marked impairment due to chronic sleep disruption, elevated cortisol levels from psychological stress, and microgravity-induced T-cell suppression. The crew finds themselves caught in a dangerous biological imbalance. Their immune systems are progressively weakening, while the opportunistic microbes sharing their small living quarters are mutating into hardier, more aggressive strains. A simple skin infection or respiratory inflammation that would be trivial on Earth can quickly escalate into a persistent drug-resistant outbreak inside the closed habitat. This ecological vulnerability exposes a fundamental flaw in artificial life support design. A closed biosphere on Mars is inherently far more fragile than terrestrial agriculture. On Earth, natural farming relies on deep ecological buffers, complex soil-food webs, natural predator-prey relationships among microorganisms, vast atmospheric volumes, and soil buffering capacities that absorb chemical shifts and disease outbreaks. On Mars, Crop production inside habitat greenhouses relies on hydroponic or aeroponic systems, utilizing ultra-refined water loops and synthetic nutrient solutions. In this closed loop, stoichiometric recycling limits leave no room for error. If a single aggressive fungal blight or mutated bacterial pathogen infects the habitat's hydroponic crop bays, there are no soil buffers or wild microbial competitors to slow its spread. A plant disease can sweep through the entire food production module in days, destroying months of calorie reserves and collapsing the habitat's primary carbon dioxide scrubbing and oxygen generation capacity. Furthermore, the absence of natural organic waste decomposers means that human metabolic waste must be processed through complex mechanical, thermochemical reactors rather than natural soil cycles. A single mechanical failure in the waste processing reactor or a sudden microbial contamination event in the water recycling loop propagates instantly across the entire life support system. The sealed biosphere is not a self-sustaining miniature Earth. It is a precarious, highly unstable biological tightrope where a tiny microbial imbalance can trigger systemic ecological collapse. As internal ecological stress builds within the habitat's closed loops, the crew's ability to diagnose and repair unexpected biological or mechanical crises is severely constrained by an absolute physical boundary. When a water recycling line clogs with antibiotic-resistant biofilm or an automated crop bay suffers a catastrophic nutrient imbalance, the habitat engineers cannot simply initiate a real-time consultation with specialists on Earth. Beyond the sealed airlocks and thick regolith shields lies an impenetrable physics barrier, the speed of light. The physical distance separating Earth and Mars prevents immediate communication, forcing the crew to manage complex biological and mechanical emergencies in total isolation. The biological paradox of the sealed biosphere transitions directly into the relentless light lag isolation of interplanetary space. Inside these subterranean habitat loops, the biological crisis expands from human tissue to the broader microecology of artificial biospheres. On Earth, human health relies on continuous microbial exchange with soil, rain, plant life, and diverse animal populations. Inside a sealed Martian habitat, this natural microbial diversity disappears. Over time, habitat air and water loops become microbially impoverished, stripping human skin and gut microbiomes of beneficial bacterial strains. This loss of microbial diversity triggers gut dysbiosis, reducing short-chain fatty acid production and impairing intestinal barrier integrity. Simultaneously, high ambient radiation levels inside habitat modules select for rapid microbial mutations. Opportunistic bacterial strains like Pseudomonas aeruginosa adapt to life inside synthetic water recycling pipes, forming radiation-resistant, dense biofilms that clog fluid conduits and resist chemical sanitation. In hydroponic crop bays, the absence of natural soil buffer capacity creates extreme ecological volatility. A minor imbalance in water recycling chemistry or the introduction of a single mutated plant pathogen can trigger rapid crop blight, destroying oxygen-producing crop decks within days. The artificial biosphere on Mars is an ecologically fragile island, where the collapse of trace microbial loops threatens the immediate survival of human occupants. This microbial impoverishment inside sealed habitats creates subtle, systemic immunological vulnerabilities in human settlers. Without exposure to diverse environmental microbes, regulatory T cells inside the human immune system lose their inhibitory training, leading to immune dysregulation, heightened hypersensitivity, and auto-inflammatory responses. Latent viral pathogens such as Epstein-Barr virus and varicella zoster reactivate under chronic physiological stress and high background radiation, shedding viral particles into habitat air loops. Simultaneously, closed hydroponic crop systems rely on fragile bacterial nitrogen-fixing consortia and artificial nutrient solutions. If toxic heavy metals or chemical oxidizers from local regolith leach into hydroponic water tanks, microbial nitrogen fixation collapses, causing rapid leaf chlorosis and crop failure across whole farming decks. Settlers are trapped inside a delicate biological loop where microbial health dictates both atmospheric purity and food security. The most profound psychological barrier dividing Earth from Mars is not measured in physical meters or radiation sieverts, but in seconds of light travel time. Because electromagnetic radio waves travel at the speed of light, approximately 299,792 kilometers per second communication between Earth and Mars is subject to an inescapable physical delay dictated by orbital geometry. When Earth and Mars reach their closest orbital approach, known as opposition, the distance between the two worlds contracts to roughly 55 million kilometers, resulting in a one-way signal latency of 3.2 minutes, or a round-trip delay of 6.4 minutes. However, as the two planets move along their respective heliocentric orbits, this distance expands dramatically. At maximum orbital separation, known as conjunction, when Mars and Earth sit on opposite sides of the Sun, the physical distance swells to over 400 million kilometers. At this extreme separation, a radio signal takes 22.2 minutes to cross the interplanetary void, creating a round-trip communication lag of nearly 45 minutes. Furthermore, during solar conjunction, which occurs once every 26 months, the Sun passes directly between Earth and Mars. For a period of roughly 2 weeks, intense solar plasma and coronal ionization completely distort and block radio signals transmitted through the solar atmosphere. During this blackout period, the Martian settlement experiences absolute electromagnetic isolation from Earth, cut off from all telemetry data, software patches, and human contact. This variable light lag completely destroys the fundamental structure of human communication. On Earth, human conversation relies on real-time acoustic feedback, subtle pauses, instantaneous emotional micro-expressions, overlapping vocal cadences, and immediate verbal responses that occur within milliseconds. This rapid feedback loop forms the foundation of human social bonding, psychological empathy, and operational trust. Across a 4 to 24 minute light lag, real-time conversation becomes physically impossible. Every video transmission or voice message becomes an asynchronous broadcast. A crew member asks a question, sends the transmission into the void, and must wait anywhere from 10 minutes to nearly an hour to receive an answer. Social neuroscientists studying long-duration communication latency note that this loss of real-time conversational cadence leads to profound psychological detachment. Over time, crew members stop sending casual, emotional updates to loved ones or mission control, as the long delay renders emotional exchanges hollow and awkward. The cadence of relationships fractures. Friends, family, and support staff on Earth become historical figures, distant entities residing in a different time domain, whose advice arrives long after the immediate emotional context of a situation has passed. The crew's psychological identity shifts inward toward their immediate habitat peers, severing the intangible emotional threads that connect them to their homeworld. This breakdown of real-time communication exposes a dangerous operational reality when a crisis occurs on Mars. Mission control on Earth is reduced to a passive observer in low Earth orbit aboard the space station or during the Apollo lunar landings. Mission control in Houston operated as an active command center. Hundreds of specialized flight controllers monitored real-time telemetry, running predictive computer simulations and issuing immediate step-by-step commands to assist astronauts during system malfunctions. On Mars, if a critical life support valve fails, a habitat pressure seal ruptures, or a medical emergency occurs, the event will be fully resolved for better or worse long before ground control even receives the initial telemetry warning of the failure. The entire traditional command structure of space exploration collapses under light speed limits. The Martian crew cannot rely on Earth controllers for operational permission, diagnostic troubleshooting, or emergency authorization. They must assume absolute operational autonomy, functioning as an independent entity that makes life or death engineering decisions without external validation. During the 2-week solar conjunction blackouts, this autonomy becomes absolute. Knowing that no message can leave or enter the planet forces the crew to confront their terrifying independence if their environmental control system fails during conjunction. No engineer on Earth can offer guidance. They are entirely on their own, marooned on a silent world where Earth is merely a faint star lost behind the blinding glare of the sun. This absolute communication isolation severely complicates daily habitat operations when critical life support machinery breaks down. On Earth, complex industrial facilities rely on extensive supply chains, specialized off-site technical support, and immediate manufacturer consultations when precision machinery fails. On Mars, every machine keeping the crew alive, from atmospheric carbon dioxide extractors to water recycling centrifuges, must be repaired using only the tools, spare parts, and diagnostic knowledge present inside the habitat. When an unexpected mechanical failure occurs, the crew cannot wait 45 minutes for diagnostic instructions from Earth engineers. They must diagnose complex thermodynamic, electrical, and fluid mechanical failures themselves under immense psychological pressure. If a critical component breaks for which no spare part exists, they must re-engineer the component using local additive manufacturing or cannibalize other non-essential systems. The psychological burden of knowing that a single incorrect diagnostic decision or failed mechanical repair will result in habitat depressurization or toxic gas buildup with no external help possible places intense, continuous stress on habitat technicians. The light lag isolation strips away the comforting illusion of the Earth support, forcing settlers to recognize that their lives depend entirely on the mechanical reliability of their hardware and their own ability to repair it. The communication breakdown transitions directly into the mechanical fragility of life on Mars. This physical separation is compounded by orbital geometry variations that systematically alter the latency of light-speed communications. As Earth and Mars move along their respective orbits around the Sun, the physical distance between the two planets fluctuates dramatically, ranging from a minimum of 55 million kilometers to a maximum of over 400 million kilometers. At closest approach, radio signals travelling at the speed of light take approximately 3.2 minutes to cross the void. At maximum separation, one-way transmission latency stretches to over 22 minutes. This means a simple question and answer requires a round-trip delay of nearly 45 minutes, completely eliminating real-time conversation and breaking down traditional operational command structures. Furthermore, every 26 months, the orbital alignment places the Sun directly between Earth and Mars, an event known as superior solar conjunction. For nearly 2 full weeks, solar coronal plasma emissions scatter and distort radio frequency transmissions, causing total electromagnetic blackout. During conjunction, the Martian habitat is completely severed from Earth tracking networks. Settlers must operate in absolute communication darkness, relying entirely on autonomous onboard systems to handle habitat emergencies, medical crises, and life support failures without a single bite of guidance from ground controllers. The psychological toll of light lag communication breakdown alters how settlers relate to Earth culture and human history. As months turn into years, asynchronous messaging replaces real-time emotional exchange. News from Earth family milestones, political events, cultural shifts arrives as recorded video files delayed by minutes or hours, stripping communications of spontaneous emotional reciprocity. Settlers gradually stop reaching out for immediate emotional validation from family members on Earth, recognizing that their loved ones live in a completely different temporal and physical reality. This temporal detachment fosters a distinct Martian subculture. The colony begins to prioritize internal social cohesion over Earth directives, developing its own dialects, idioms, and operational norms. The light lag barrier is not merely an engineering limitation. It is the catalyst that severs psychological dependence on Earth, allowing a new planetary identity to emerge. Human existence on Earth is sustained by colossal, self-healing natural systems, the hydrological cycle, atmospheric convection, oceanic carbon sinks, and biological food webs that operate continuously without human intervention. On Mars, human life is sustained entirely by complex, fragile mechanical hardware. Inside a Martian settlement, every breath of oxygen, every drop of potable water, and every degree of internal thermal regulation is actively manufactured by life support machinery operating under extreme physical stress. Oxygen production relies on devices like MOXIE Mars, Oxygen ISRU experiment, which scrub atmospheric carbon dioxide at 6 millibars pressure, compress the gas, heat it to 800 degrees Celsius inside solid oxide electrolysis cells, and electrochemically split carbon dioxide into oxygen ions and carbon monoxide waste. Water recovery relies on multi-stage environmental control and life support systems ECLSS using vacuum distillation centrifuges, catalytic oxidizers, and high-pressure reverse osmosis membranes to recycle urine, sweat, and atmospheric humidity into drinkable water. Atmospheric pressure regulation requires continuous mechanical pumping to scrub carbon dioxide and maintain a stable 70% nitrogen, 30% oxygen gas mix at sea-level partial pressures. If any of these mechanical systems suffer a catastrophic component failure, human life inside the habitat begins a rapid countdown toward extinction. There are no natural ecological buffers. Life on Mars is an artificial, high-pressure industrial process that must run 24 hours a day, 365 days a year, without a single total systemic pause. This mechanical life support infrastructure operates under continuous aggressive attack from the Martian environment. Low atmospheric pressure, extreme thermal swings, and toxic perchlorate dust work in tandem to accelerate mechanical wear on mechanical valves, pump impellers, and pressure seals. Daily temperature fluctuations on the Martian surface, plunging from a daytime high of plus 20 degrees Celsius to a nighttime low of minus 125 degrees Celsius, cause severe thermal expansion and contraction cycles across exterior structural joints, hatch seals, and fluid lines. This thermal fatigue induces microfractures in metal alloys and degrades synthetic elastomer seals, making them brittle and prone to vacuum outgassing. Simultaneously, ultra-fine perchlorate dust suspended in the atmosphere bypasses intake filters, entering mechanical compressor pumps and valve seats. The razor-sharp silicate particulates score precision-machined valve surfaces, cause mechanical seals to leak, and contaminate lubricating oils. Inside water recycling systems, high concentrations of urea, inorganic salts, and aggressive biological biofilms corrode titanium heating elements and clog centrifuge membranes. Valves that would operate reliably for decades on Earth fail within months on Mars due to the combined action of particulate abrasion, chemical oxidation, and extreme thermal cycling. The machines keeping the crew alive are constantly grinding themselves to pieces from the inside out, demanding continuous mechanical intervention. This reality forces a fundamental reevaluation of what living on Mars actually entails. Popular cultural narratives portray planetary settlement as a heroic era of outdoor exploration, scientific discovery, and agricultural expansion. In engineering reality, living on Mars is less like living in a frontier pioneer town and more like living inside the engine room of a damaged submarine. Field studies of life support engineering indicate that habitat technicians and crew members must dedicate up to 80% of their available working hours to routine maintenance, diagnostic troubleshooting, component replacement, and system cleaning. Science EVAs and geological research are constantly postponed because a primary oxygen compressor valve is leaking, a water distillation centrifuge balance is failing, or an atmospheric carbon dioxide scrubber bed requires manual chemical regeneration. spare parts logistics present a critical vulnerability. Because shipping replacement components from Earth requires a minimum of 7 months transit time and can only occur during 2-year orbital transfer windows, the settlement must maintain absolute manufacturing self-sufficiency. If a specialized high-pressure valve casing cracks and no direct spare exists, the crew must rely on metal 3D printing or manual lathe machining using recycled hull alloys. The continuous burden of mechanical upkeep turns human settlers into permanent industrial maintenance workers, whose daily survival depends entirely on their ability to stay ahead of mechanical entropy. This perpetual mechanical maintenance workload permanently reshapes the biological and cultural trajectory of human settlers. Living under the constant threat of hardware failure forces the colony to adopt rigid, military-grade operational protocols and extreme resource rationing. Every litre of water, gram of oxygen, and watt of electrical power is tracked by automated resource ledgers. Spontaneity, personal leisure, and non-essential activities are strictly subordinated to the relentless maintenance schedule required to keep the life support machinery running. As months turn into years, this total integration of human life with mechanical hardware alters human psychological identity. Settlers cease to view themselves as temporary Earth explorers visiting an alien world. They become an engineering caste whose culture, social habits, and daily rhythms are dictated by the thermodynamics of their machines. They develop an intimate, almost ritualistic relationship with the habitat's pumps, scrubbers, and pressure hatches, knowing that their collective survival depends on the structural integrity of every weld and seal. This absolute reliance on mechanical life support, combined with low gravity, radiation shielding, and genetic isolation, accelerates a profound transformation. The mechanical fragility of life on Mars completes the separation from Earth, setting the final stage for generational biological and cultural speciation. The mechanical survival struggle transitions into the Martian divergence. The operational burden of maintaining this mechanical infrastructure dominates daily life inside the settlement. Life support systems on Mars cannot operate as passive appliances. They are complex thermodynamic factories that require constant maintenance, recalibration, and repair. Solid oxide electrolysis units extract breathable oxygen from atmospheric carbon dioxide by operating at temperatures exceeding 800 degrees Celsius. This intense thermal cycling, combined with fine dust ingestion through intake compressors, causes rapid thermal stress cracking in ceramic catalyst tubes and mechanical seal failure in gas pumps. Vacuum distillation centrifuges used for urine reclamation suffer from mineral scaling, requiring technicians to handle concentrated chemical descaling agents inside enclosed habitat volumes. Catalytic oxidizers scrubbing volatile organic compounds from habitat air gradually lose catalyst reactivity, requiring high-temperature regeneration. Because spare parts shipments from Earth occur only once every 26 months and carry immense launch costs, settlers cannot simply replace worn components. They must repair damaged impellers, reseat pitted valves, and machine custom metal fittings using local additive manufacturing systems. Over 75% of crew duty hours are consumed by mechanical diagnostics and hardware maintenance, transforming the settlers into full-time industrial technicians whose lives depend on the continuous operation of their machines. The mechanical vulnerability of life support hardware forces the adoption of strict redundancy design and local resource utilization protocols. Every critical life support loop from Sabatier reactors producing methane fuel to electrochemical oxygen generators is designed with double or triple mechanical redundancy. However, operating multiple redundant units accelerates spare parts consumption and places extreme demands on local machine shops. Habitat technicians must continuously refurbish worn pump impellers, rewire overheated motor stators, and resynth polymer seals using local chemical feedstock extracted from atmospheric carbon dioxide and subsurface ice. If a primary water recovery centrifuge suffers bearing seizure during a dust storm, technicians cannot wait for replacement assemblies from Earth. They must tear down the high-speed centrifuge inside a cleanroom module, remachining tolerances by hand while habitat water reserves dwindle. Survival on Mars is an unyielding exercise in industrial maintenance, where life is sustained only by the continuous deeply skilled labour of crew technicians. When all the physical, biological and psychological forces of the Martian environment act upon a human population across decades, an inevitable biological transformation takes hold. The first settlers on Mars will not remain Earthlings living on another planet. They will undergo profound phenotypic and structural adaptation. Under the continuous influence of 0.38 Earth gravity, osteoblast activity slows down while osteoclasts continue to resorb bone tissue, permanently restructuring the human skeleton. Spines elongate as intervertebral discs decompress, increasing average adult height while reducing bone mineral density in weight-bearing bones like the femur and pelvis to a new, lower structural baseline optimized for partial gravity. Muscle fiber composition shifts, favoring fast-twitch athletic fibers over heavy anti-gravity postural fibers. Concurrently, breathing atmospheric air maintained at lower partial pressures and higher carbon dioxide fractions expands lung residual volume and alters blood hematocrit levels. The internal gut microbiome, isolated from terrestrial microbial reservoirs, establishes a specialized, highly efficient symbiotic equilibrium adapted to hydroponic diets and sterile habitat modules, combined with altered circadian gene expression driven by the 24-hour, 39-minute Martian soul. The human body undergoes a comprehensive physiological recalibration. Long before genetic mutations alter the DNA sequence, phenotypic plasticity permanently reshapes the human form. This biological adaptation exposes a terrifying physical threshold for settlers who spend years adapting to Mars. Returning to Earth becomes not merely difficult, but biologically dangerous or physically impossible. After years of bone structural remodeling, muscular atrophy, and cardiovascular recalibration under 38% gravity, stepping back into Earth's full 1G environment would subject the body to excruciating physical trauma. Weakened femurs and spinal vertebrae would face immediate fracture risks under triple the load they have adapted to support. The cardiovascular system, calibrated to push blood against a weak gravitational pull, would be unable to maintain cerebral perfusion pressure against Earth's heavy downward gravity vector, causing chronic orthostatic syncope and severe vascular collapse. Furthermore, the immunological divergence is absolute. Having lived inside a hypersanitized habitat with an impoverished microbial ecosystem, a Martian settler's immune system would lack protective antibody titers against thousands of common terrestrial viruses, bacteria, and allergens. Stepping off a spacecraft on Earth would expose them to a barrage of mild terrestrial pathogens that their weakened, specialized immune defenses could perceive as lethal threats. Mars is not a temporary assignment from which explorers can seamlessly return. It is a one-way biological door. Settlers who commit to Mars commit their bodies to a permanent physical separation from their world of origin. This permanent biological separation redefines human colonization from a simple geographic expansion into an evolutionary speciation event. On Earth, human migration across continents was bounded by a shared atmosphere, a constant one-gravity environment, and continuous genetic exchange. On Mars, physical isolation, radiation-induced mutation rates, and partial gravity establish the precise conditions required for rapid biological and cultural divergence. Over generations, children born on Mars developing from conception under 0.38 G and elevated ambient radiation will possess distinct skeletal proportions, altered cardiovascular structures, and unique metabolic pathways. Culturally, the divergence will be even more immediate, a society living underground, communicating across light lag delays, measuring time in 39-minute sols, and managing daily survival through life support mechanics will naturally abandon terrestrial cultural paradigms. A new Martian language will emerge, filled with specialized technical idioms, altered vocal cadences adapted to lower atmospheric pressure, and metaphors rooted in habitat engineering rather than terrestrial nature. Earth will cease to be a homeworld. It will become a mythical ancestral origin, a bright blue star in the evening sky remembered only through historical archives and delayed video signals. The settlers will no longer identify as humans on Mars. They will become Martians, a distinct branch of humanity born of an alien world. Understanding the true physical reality of Martian settlement exposes the profound uniqueness of our origin and the true cost of becoming a multiplanetary species. The journey to colonize Mars is not a triumphant technological victory over nature, but a quiet, sobering lesson in human vulnerability. It reveals that Earth is not merely a temporary cradle that humanity can effortlessly outgrow, but extraordinarily rare biological sanctuary whose dense atmosphere, protective magnetosphere, vibrant natural ecosystems, and perfect 1G environment were meticulously matched to our biology over billions of years of evolution. Every challenge waiting on Mars, from toxic perchlorate dust and subatomic cosmic rays to light lag isolation and mechanical life support fragility, reminds us that living anywhere else in the cosmos requires trading our biological freedom for an artificial existence inside a metal machine. Yet, despite these immense physical barriers, the human drive to reach outward remains unextinguished. As the first settlers look out through multi-layered quartz viewports at the blue Martian sunset, watching Earth vanish into the butterscotch sky, they will embody both the terrifying cost and the quiet splendor of human adaptability, stepping forever out of the terrestrial cradle to forge a new branch of human life among the stars. This evolutionary divergence represents the ultimate outcome of long-term planetary settlement over generations. The continuous selective pressures of 38% Earth gravity, baseline ambient radiation, synthetic atmosphere composition, and total environmental isolation will fundamentally alter human biology. Bone trabecular architecture will adapt to lower load vectors. Cardiovascular stroke volume set points will recalibrate to lower hydrostatic pressures, and thoracic muscle mechanics will adjust to pressurized habitat environments. Epigenetic methylation patterns will stabilize around low-dose radiation responses and modified dietary inputs, creating distinct developmental trajectories for children born on Mars. Culturally, Martian society will develop its own linguistic cadences, social values, and technological traditions rooted in collective mechanical survival and subterranean living. Settlers will no longer feel a physical or psychological connection to the high-gravity, liquid water world of their ancestors. They will become a distinct branch of humanity, a species adapted to the cold, dry, low-gravity reality of Mars. Their existence will stand as proof that moving to another planet is not an extension of terrestrial life, but the creation of an entirely new form of human existence among the stars. This generational transformation culminates in a permanent evolutionary divergence that redefines humanity's place in the cosmos. Children born on Mars will grow up under 38% gravity, inside subterranean habitats shielded from cosmic rays, breathing synthetic atmospheres and eating hydroponic crops. Their physical bodies will reflect these environmental pressures longer: thinner limb bones, adapted cardiovascular set points, modified immune responses, and unique pulmonary capacities suited to habitat pressure regimes. They will look upon photographs of Earth's blue oceans, green forests, and open skies not with nostalgia, but with the curiosity one reserves for an alien world. Earth will be to them a high-gravity ocean planet of their ancestors, a beautiful, heavy world whose crushing gravity and unshielded atmosphere they can never safely visit. the first settlers on Mars will have accomplished something far grander than building an outpost. They will have birthed a new branch of the human species, permanently expanding the horizon of conscious life into the cosmos.